So, trig functions of general angles. Now this looks funky. We've got x and y and r and all this weird stuff. So let's clean this up first into language that we understand. So instead of calling this side x, we're going to say x is adjacent. Because if I look at this point over here on this little graph that's done, x, y, x would be along the x-axis. And if this is my angle measure, that's the adjacent side. So calling it adjacent isn't a stretch. So then y would be our opposite side. Because again, if I'm labeling this, you're like, Hardy, how are you just making this up as you go? I'm not. Because to get to this point, I went left on the x-axis this many. And then I'd go down for this particular one. There's the opposite. And so then we finally finish up the end. R is my hypotenuse. So here's why I think that makes it a little bit easier in our brains. Because now go back and look at these. You're like, oh, opposite over hypotenuse. Adjacent over hypotenuse for cosine. Opposite over adjacent for tangent. And so it's all the same trig functions we learned earlier, just looking at it a weird way. So if you're given coordinate points for something, you just got to kind of remember this is adjacent, this is opposite. Like, how am I going to keep that straight? A comes before O in the alphabet, just like X comes before Y. And we'll go over that some more as we go, but that's the main thing I want to keep track of here in my head. So let's actually do something with this. Am I going to play with all these as much? No, but I like having them there just to let me kind of see this and think it through a little bit. So here's all you really have to remember. Let's really simplify. You're given a coordinate point, okay? Do I need to make a triangle? I don't think we do, and here's why. If this is adjacent, and this is opposite, whenever you're given a coordinate point, the only thing you need to figure out to be able to do all your trig functions is the hypotenuse. And we know how this works, because if I've got a triangle, and I have this side, and I have this side, and I need this side, how am I going to figure it out? Pythagorean theorem. So we're going to use the Pythagorean theorem to find the hypotenuse. And once we have that, we should be in pretty darn good shape. So if you remember back to when you were doing stuff in geometry or possibly even in Algebra 1 class, you may have talked about things called Pythagorean triples. But if you didn't, that's not a bad thing. Like if you did, you might remember that a 5, 12, 13 triangle is a thing. I'd know my hypotenuse right away. But if not, it doesn't take that long to figure out our hypotenuse here. Bust out the calculator and take the square root of whatever we get. So now I got my hypotenuse. I got it all. And so when I go to build all of these, now I still have to remember what goes with what on my trig functions. I mean, that's kind of a given. But here, for instance, we got opposite over hypotenuse. We got adjacent over hypotenuse. And we've got opposite over adjacent. And so then to get their inverses, remember when you're trying to remember between now which one of these goes with which, they never start with the same letter. So secant and sine, cosine, they can't go together. It's always that opposite one. And we're just taking the reciprocal of that fraction that we had initially. And we're done. So when you're doing these, even if, let's say we were doing 3, let's throw a small twist in. Still adjacent, still opposite. Like, what about that negative? Is that going to mess things up? It shouldn't. Your hypotenuse will always be positive. Even if they're negative. Here's why. As long as you remember one small detail. When you're squaring these, especially if you see a negative, using parentheses is a good plan. Because otherwise, you're going to get a different answer. So that is very different from this. Like, I can't do that anyway. That doesn't make any sense. So make sure we get that. And then again, same thing. Do I know my stuff? What about the negative? Yes, you keep the negative. You're going to see why that is here shortly. But if it has a negative in the coordinate point, you've got to keep it. Bless you. Opposite over adjacent. Then all the flipping. And yeah, if you wanted to put the negative on the 15, just put that in the denominator, you could. But normally we just put negatives out front, which is why I did that. But if it's negative in one of these, it will be negative in its inverse as well. Positive is positive, negative is negative. So now, let's throw one more twist in. So we've seen where it comes out really nice. We've seen where it's still pretty nice. We've got some negatives, but whatever. What if I run into my hypotenuse and it's not pretty? So let's see here. Let's see here. 64 and 144. 208. Now, Hardy, do I get to go to a decimal? No. Exact values. No decimals. So hang on a minute. So h squared is the square root of 208. Uh-oh. We got to break it down. Okay? If it's breakdownable, which this one is, we need to break it down. So, let's see here. Oh, what's going to go into 208? I'm going to think big first and then work my way down here. Okay, nope. 16, I'm being told. Whoops, hang on. I got to type in the right number. I'm good. That's good. 16 and 13. Okay. So my hypotenuse is 4 times the square root of 13. Oh, boy. So we start to set these up. Okay. I know some of you are speed demons with making these conversions. I wouldn't go quite that crazy on this. Here's why. So sine is opposite over hypotenuse. But, yeah, we got to clean this up. There's no radicals in the denominator. So since this is an example in here, I want to show every step of this. Since this can be reduced, I'm going to go ahead and do that. So that would be 3 over the square root of 13. 12 divided by 4. And then our shortcut to simplifying so you don't have to write out the whole rationalization, remember, is move the radical to the top and lose the radical in the denominator. So the square root of 13 to the numerator, just lose the radical. That's your simplified version of your sine. And so once you see that on the first one, it shouldn't be bad on the others. So like here, Negative 8 over 4 square root of 13. My apologies for having to write small. Should have spaced these out a little more. Hang on. I'm going to try and jumbo size. It's not your eyes, people. It's not your eyes going bad. So we got negative 8, my adjacent, over my hypotenuse. Hardy is going to make a little drawing down here because this is going to get a little crazy otherwise. Reduce the part I can. And then again, to get it rationalized, now put that back up here. Radical to the numerator. Lose it in the denominator. We will not have to do all this work when we do the inverses. Trust me on this one. And then tangent at least is easy. Opposite over adjacent, I just got to reduce the fraction. So negative 3/2. Now some of you might be wondering, okay, Hardy, you just said we're not going to have to do all this rationalizing stuff over here. Explain that. When you flip this, there's going to be a radical in the denominator. Why are you saying that we're not going to have to do that? Because we're going to be smarter than that. We're going to come to the one right before it, before we rationalized it. This is why I like to see it. If I take that fraction and I flip it, I don't have to rationalize anything. And it's simplified. If I flipped this over and rationalized it, yes, I'm going to be crazy enough to show you. So if I took this, okay, my answer over here, and I said, well, that's cosecant. So that is going to get flipped. So let's flip it. Now I got to move that to the top. Oh my gosh, this is a pain in the butt. That goes away. Oh. 13 over 39 reduces to 1 over 3. So I end up in the same place. Keep life simple on yourself. Don't make yourself have to do it twice, because that'd be crazy. Same thing here. If you go ahead and simplify this before you rationalize it, you're not going to have to do it over here. And then the tangent we don't worry about at all. So there is a little bit of thought process when you get stuck into these. But again, at worst case scenario, show me that first step. So at least if you get that on the test, I can give you a little bit more as far as points go. Okay? That's as crazy as this gets. So let's look at one more like that, just to kind of let our brains get wrapped around it, and then we'll put in our last couple of little pieces here. So adjacent and opposite. Okay. Hypotenuse. 1 squared is 1. So 1 plus 4 is 5. So my hypotenuse is the square root of 5. All right, let's see what fun we get this time. So opposite over hypotenuse. Adjacent over hypotenuse. Opposite over adjacent. I'll simplify that. So, oh, this one is not going to be as bad at all. All right. Radical to the top. Lose it down below. Nothing else reduces. All right. Radical to the top. Lose it down below. Square root of 5 over 5. But again, even if you see that, remember, you want to put the original one here first, or at least be thinking it, because now when you go to do the inverse, if I take the original problem I did and invert it, I'm good to go. I don't have to do anything. Take the original and invert it. I guess I didn't need to do that. I could have just kept that as the square root of 5. Not bad if you put it over 1. And then 1 over 2 for my cotangent. So rationalizing probably is the only thing that would be kind of screwy when we're dealing with that. But otherwise, it's not going to be anything that's too terribly awful when we're going through with those. But again, practice will make that easier as you go. Okay, I'm going to zoom back out a little bit here so we can see what we're up against. Now, what happens if when you're given your coordinate point, the coordinate point is on an axis? It's on the x-axis, it's on the y-axis. Like, how is that going to mess with me when I'm looking for all these values? Well, we're not going to change a darn thing from what we're doing. So, here's the way I want you to kind of think of this. When you're looking at these, I know this says R, but I'm going to actually change values on things to make it a little more concrete. We're going to look at all these R's as though they're ones. We're going to make this like a unit circle. So, by doing that, I'm looking at this and I'm saying, okay, this is still adjacent, this is still opposite. That has not changed. My hypotenuse will still be 1 squared plus 0 squared. So my hypotenuse would be the square root of 1 because it's 0 squared plus 1 squared. So I've still got all the same stuff. So here now, at 0 degrees, because I didn't rotate at all, my sine is still opposite over hypotenuse. You're like, wait, it could be 0? Yeah. Cosine is adjacent over hypotenuse. And tangent is opposite over adjacent. So for any of these, when you run into them, we're going to run it back that same way. Adjacent and opposite. Your hypotenuse is still going to be 1. It's going to be for all of these. That's the insider hint here. On a quadrantal, just means it's right on an axis. This is always going to be the case. And so now, sine, opposite over hypotenuse. Cosine, adjacent over hypotenuse. Tangent, opposite over adjacent. That's not defined. We can't do that. You can't divide by 0. So you will run into some situations with this. And there are ways to check it on the calculator. You could type it in, and it'll just give you an error message. You're like, why don't we just do that? Because there's going to be some times and some places that using the calculator is not going to be helpful. So that's why we just kind of get away from it right away. So you're like, so this is just going to be the same old boring thing all the way around with these. Yep. And it's also going to start getting you to think a little bit about that unit circle that I said we'll be dealing with at the start of next section. So again, opposite over hypotenuse, adjacent over hypotenuse, opposite over adjacent. And again, always got to tell me on this, is it 0 or is it undefined? Because I want to know that you know. Hopefully you know, but just in case, we got to be sure. Adjacent, opposite, hypotenuse is always the same. Opposite over hypotenuse. Adjacent over hypotenuse. Opposite over adjacent. Now again, is that something you necessarily have to memorize? No, but if I were to ask you a question like, hey, name sine, cosine, and tangent when it's 90 degrees, being able to either in your head draw this little picture, okay, 90 degrees is straight up. I went up 1 on y, but I didn't go left or right for x. Or if I asked you on 180, okay, now I got to think again on a graph. opposite instead of you having to be given that point. So we want to start making those connections as we start to finish this. Okay? We're almost there. We're almost there. Hi, Hardy. Oh my gosh, Hardy. What is this craziness? Okay, we're going to simplify this too. That's why we do this. So now, we have this thing called a reference angle. Not coterminal like yesterday, plus or minus 360. This is different. This is where your reference angle is the acute angle, always acute. Always going to be less than 90 degrees. Formed by the terminal side and the nearest x-axis. Okay? That's the key to remember here. We're always going back to the x-axis. So I've always found it's easier, instead of memorizing all these different little things per quadrant and stuff, is to just get into it and use a little common sense. So here's what I mean. We're going to come down here. It says sketch an angle. Find its reference angle. Okay, we'll get a little practice in here while we're doing this. We'll start with an easy one because it's between 0 and 180. Again, if you need one of these little stinkers, they're back on the back table. So 135, it's positive, so we'll stay on the inside ones. There's 135. Get that in here. Show our curve to show that it's counterclockwise and positive. So, you're like, okay, we got this angle. We've done this before. What's this reference angle thing? Okay, here's the question you have to ask yourself. This is all you've got to do this. How far, in degrees of course, so two things on a reference angle. First, how far am I away from the nearest x-axis? Because that's going to be your reference angle. And also, when you're looking for a reference angle, they are always positive. I don't care if you're going forward, back. It does not matter. They're always positive. Okay? So, just to kind of keep some things straight. So you're like, okay, how do I know how far it is from the nearest x-axis? So, what I like to do, and this is how I don't screw this up, I always like to label my x-axis. I'm like, okay, 0, 180, 360. I'm not going to go further than 360. So right here is 135. So visually, I can look at this and go, okay, if I'm here, here's the nearest x-axis, right? So that's how much further I got to go. And I'm just like, oh, so 180 minus 135 is 45 degrees. That's my reference angle. Because you're going to get to a point when we get in the middle of the next part of the unit that knowing that it's a 45-degree angle, I said, hey, it's the sine of 45, what is it? You're going to rattle it off because you're going to know what it is. It's going to make things easier and go faster. So we're just kind of setting up for that right now. So our main job here, let's see here. 0, oh, I'm going to set myself up. That's okay. 200 degrees. Okay, that's not on this. So, we're going to start. So we got 90. We got 180. But I need another 20 to get to 200. We stopped on the x-axis. So line up on the x. And get you another 20 right there. So there's my 200. Nearest x-axis, you do not have to keep going counterclockwise. You can go backwards. It's true. So here, you're like, well, that's the nearest one. So right there would be how I'd get back to my reference angle. So since I'm going clockwise now, is it negative? No, it's always positive. That's my reference angle. So that's one thing I've got to kind of get over as I'm dealing with reference angles. And okay, Hardy, now what? So 2 things to note on our radian here. First time out of about 1 billion you will hear me say this over the next probably month. If you start in radians, you will end in radians. Now, that does not mean you have to do radians all the way around here. That might be a little over the top. But I'm just putting that out as a reminder to try and save you later, because you're like, okay, I'm not going to change that on here because then I'm going to be tempted to do something bad. So 5 times 180, because that's what pi is when we're talking in radian speak, divided by 3. This is a 300-degree angle. Maybe I'll write it really tiny over here so I know it, but I'm not using degrees because we're not speaking degree on this question. So I got to make a 300-degree angle. So all right, 90, 180, 270. I need another 30 to get to 300. I stopped on the y-axis, so that's where I'm going to set this up. Because I got to get my extra 30 here. So there's my 30. So now comes the challenge. I know this is the nearest x-axis. But here's the game. You're like, okay, so the nearest x-axis is 360. So you're like, all right, 360 minus 300. Hardy, my reference angle is 60. Start radian, end radian. If you're going to go to degrees, fix it. We know how to convert to get rid of the degrees. 60 over 180 is 1/3. Pi over 3 is my reference angle. When we speak radian, we end radian. When we speak degree, we end degree. That's the rules. No going between languages. Not a fair thing to do. You're like, oh my God, it never ends, Hardy. This is actually the last piece. There's just a lot of pictures with the last piece. So that's why we got to play it. All right, the last piece to play pictures with. This is why we get a work day tomorrow, because Hardy drive you crazy today. Okay. Instead of, again, going through all the different pictures and things, which are good, they're solid, they're nice to have, but here's the thing. We want to keep this simple again. So I'm going to roll down a little ways here, to this little chart here. All right, the quadrant chart. All students take calculus. You're like, what is that? What does that mean? Okay, any graph is broken up into 4 quadrants. 1, 2, 3, 4, like a big C shape. Within those quadrants tell you the signs of all your trig functions, okay? This is strictly for the signs of my trig functions. That's all I need this for. So here's how this works, and here's where this little all students take calculus mnemonic comes into play. In quadrant 1, everything is positive. Sine, cosine, tangent, all their inverses, everything's positive and happy between 0 and 90. When we get to quadrant 2, only sine and its inverse cosecant are positive. Everything else is negative. Tangent's negative, cotangent, secant, cosine, all the things. They all become negative. So that's the S here, that sine is positive. I come to quadrant 3, and again, between 180 and 270. Tangent and cotangent is the only thing that's positive. There's the T. T for quadrant 3. And then we wrap up. Quadrant 4 is cosine and secant, hence the C. So this just tells me, depending on what degree measure it is, what quadrant is it in, what sign is it going to be. So when you're trying to evaluate and get an exact value, no decimals, we're going to find the reference angle. We're going to use special right triangles. Oh, Lord, here they come again. We're going to use special right triangles, and then we're going to use these to figure out the sign. So here's how this works. You're like, oh my gosh, already this is good. Okay. This is how this rolls. Let me break this off. That's why they're giving you a break, spring break after this and the timing of this. You're going to need it. Okay. Job number 1, reference angle. Remember, with your reference angles, you're basically asking yourself, because these are all the x-axis values, which one is closest to the angle they're giving me? Subtract it. So you're like, okay, so the closest one's 180. So 180 minus 150 is 30 degrees. Okay, there's my reference angle. Now, and you might need to draw yourself a picture. I don't know. Maybe you've got this locked in. I couldn't tell you. So here, since my reference angle is 30, I'm going to be dealing with a 30, 60, 90 triangle. 1, square root of 3, 2. Those are the exact values. I don't have to play the x game with these. So I go to that and I go, okay. So the sine of 30 degrees, opposite over hypotenuse, is 1/2. The only thing left I have to figure out now is, okay, 150 degrees is in quadrant 2. So let's see here. All students take calculus. Quadrant 2 is the sine quadrant. It's positive. I'm done. That's the game. Knowing your special right to get the exact value, knowing your quadrant to get the sign. That's it. And again, as we start to get used to these, this is going to go really fast. Now, if it's a quadrantal, you're like, well, how do I know that? If it's on an axis, 0, 90, 180, 273, if it's a 90-degreer, in any way, shape, or form, it's quadrantal. So I think about it for a minute. I'm like, wait, 90, 180, 270. I didn't go left or right any, and I went down 1. Adjacent, opposite. This is where all this stuff comes into play. My hypotenuse is 1, because it always is on a quadrantal. I got everything I need now. Adjacent over hypotenuse. I'm done. You're going to come to love quadrantals when they show up, because there's going to be no thought process to them. It's just, which one is it? Pluck it off and deal with it, okay? I'm going to bounce around a little here, because I know I'm doing okay there time-wise, but I'm like, okay. Oh, Hardy, radians, seriously, dude, come on. All right, 4 times 180 divided by 3. So this is the cosine of 240 degrees. Okay, let's see what we got. 240. Let's roll this through. Closest x-axis is 180. So 240 minus 180. 60 degrees. There's my reference angle. So I need the cosine of 60 degrees. Adjacent over hypotenuse. Okay. But, which sine is it? 240. So let's see. 90, 180. 240 is over here somewhere. That's the tangent quadrant. This is not tangent. It has to be negative because we're in quadrant 3, And that's not a happy place for cosine. And I play it out. So, I need to find a 45, don't I? I need to find a 45. Where's a 45? There's a 45. Ooh. Cotangent of 135. Okay. Play the game. 45 degrees. All right, 45 degrees. Oh my gosh. 45, 90. 1, square root of 2. Gotta know your special rights. So you're like, all right. Hardy, now wait. Hardy, what are we doing? Cotangent, well, what the, okay, think about it. Tangent is opposite over adjacent. So cotangent is adjacent over opposite. It's the inverse. Well, does it really matter here? No. It's still 1 over 1, Hardy. So, okay. Now, 135 degrees. It's over here somewhere. Is this the tangent one? Nope, that's the sine one. It's negative because I'm in quadrant 2. If you left, yeah, that's fine. Or if you just put -1, that's fine. Yeah. So, last one to play with, because I haven't seen us deal with a negative yet. We need to deal with a negative. Hardy, -30. Well, here's the good news. -30, that's pretty close to 0. So my reference angle is 30, because, well, that kind of makes sense. So I'm like, okay. So I need the tangent of 30 degrees. Let me get my little drawing. Again, this wouldn't be a bad idea when you get to the test to write these on the top the minute you sit down. Just saying. Just saying. Okay, so the tangent of 30. Opposite over adjacent. All right, we're going to have to fix this. Opposite over adjacent. Radical to the top. Lose it down here. That's nice. Now, -30. Remember, other way, -30 is going to be down here somewhere. But that's the cosine world. We don't want cosine world. We're a tangent. And I'm rolling. So this, again, is why we're setting this up the way that we are time-wise and why I'm not trying to speed to this test a day earlier. I want you to have time, especially in class where you can bounce stuff off of me, to be able to deal on 5 or 6, odd, even, and then have a full day to still work on test stuff and spiraling and going back through and feeling comfortable before you get jammed into a test here. But you've got to, especially on this section, you have got to do the practice and check your answers, not just do something and write it down. Otherwise, that can get you into a sticky situation.